Welcome back everyone. In this lecture actually I will give you the definitions of this solvable and nilpotent Lie algebras, which are very important classes of Lie algebras. Okay. So, we will see later why they are important, but let us first see the definitions and some of the basic properties. So, we will actually begin with some examples to motivate these concepts. So, first let us look at this Heisenberg algebra. Okay. So, let me use this notation H3 to denote 3 dimensional Heisenberg, because later I will be actually telling you some higher dimensional, later I will be talking about some higher dimensional Heisenberg. So, it is better to use this notation H3. So, this is the Heisenberg, 3 dimensional Heisenberg, okay. The 3 dimensional Heisenberg Lie algebra. So, note that this is spanned by 3 elements which we called it as x, y, z. So, this z is being central, and whenever you take the bracket x, y you should get z. So, this is the definition. So, now you can easily see that if you compute the derived algebra of this, okay, which is H3 bracket H3. So, that will be just only one dimensional, okay, which will be span of C Z, because all other elements will get vanished. So, now again if you take one more bracket, like if you call this is H31, and then if you take again another bracket with itself, okay, again the second derived thing. So, that will be 0. So, this is something very important property, okay. Somehow this Heisenberg, even though it is not abelian, but it is not too far from being abelian, okay. If you take successive these derived algebras, then at some point you are getting 0, okay. It is actually happening very quickly, because this is 3 dimensional Lie algebra, it is so small. So, when you take this derived algebra second time, that time itself you are hitting 0. So, this is something actually motivates us to define what is called solvable Lie algebra. Okay. So, let us look at the definition of solvable Lie algebras. So, we can also see one more example maybe like so that is again very important class of solvable Lie algebras. Okay. So, let us look at that example also. So, you take this what is called this upper triangular matrices, okay, the set of all upper triangular matrices. So, then it is not hard to see this is actually spanned by the following elements E I J. So, these are all the elementary matrices such that 1 less than or equal to I less than or equal to j less than or equal to n. So, with this restriction you get the spanning set of this. So, in particularly what is the dimension of this? Okay, let us use the same notation. So, the dimension of this T and C is nothing but 1 plus 2 plus etcetera plus n, because everything on the diagonal will contribute. So, that is n, the very first off diagonal will contribute n minus 1 and so on. Then you hit the last off diagonal and then the corner. So, this will be 2, this will be 1. So, this means so you will be getting 1 plus 2 plus etcetera plus n as dimension, which is nothing but n into n plus 1 by 2. So, this is the dimension of this Lie algebra. So, now let us try to compute this commutator. Okay. So, if you compute the commutator you can see. So, let me call it G. to simplify the notation. So, then let us compute this G 1. So, it is the commutator G G. So, it is not hard to see this is actually exactly the strictly upper triangular matrices. Okay. So, this is the set of all strictly upper triangular matrices. Okay. In particularly, if you take the spanning set of this G 1, so you can easily see that. So, this is spanned by the following elements again E A J. So, now we can say this I will be never equal to j. So, this is 1 less than or equal to I will be strictly less than or equal to n. Okay. But we can actually tell in terms of what is called level of this EAJ. So, it is easy to define it for EAJ. So, if you call the level of EAJ to be j minus I. So, level means it is kind of some kind of non-negative integer that you associate with each element, and then based on that level you just induct. Okay. So, for the inductive purpose we use this concept of level. So, if we define this to be j minus I, you can see that this is always greater than or equal to 0. So, now what it says in terms of level. So, this is spanned by all this EIJ of level. So, that is j minus I at least 1. Okay. So, now I will leave it to you to check if you compute what is called this G bracket 2, which is the derived algebra of G 1. So, then one can prove that it is again spanned by E A j of level j minus I, which is greater than or equal to 2. Okay. So, this 1 can be reinterpreted as 2 power 0. So, this actually somewhat allows you to actually make a conjecture, and again which is not very hard to prove. So, I will leave it to you to verify. So, this is something I leave it to you. So, you verify that if you take this G I, which is by definition inductively defined as G I minus 1 and then G I minus 1 bracket. So, which is the derived algebra of G power bracket I minus 1. So, which is spanned by E I j of level at least 2 power I minus 1. So, in particularly you can easily see that whenever you take this successive derived algebra or the brackets, okay, if you look at pictorially what is happening. So, you have this upper triangular matrix. Okay. So, this is just filled like this. So, then if you take the derived algebra, so this is G. So, then what is happening to G 1? So, in G 1 all these diagonal entries are becoming 0. Okay. So, then you get this. So, then if you take again the derived algebra, then you can see that this is actually moving up. So, you get this is 0 and then the first off diagonal entry is also 0. So, then you start getting this star. Okay. So, this will be the G 2 and so on. So, that means every time you take this derived algebra, so you will start filling zeros for the off diagonal entries, okay, and it is actually moving in the diagonal direction. So, that actually tells that if you take this G power I for sufficiently large I, that will be 0. Actually, the I also can be determined very explicitly using this level. So, whenever 2 power I minus 1 is greater than n minus 1. So, then you have this thing 0. So, this is example suggests if we actually take this successive derived series, then at some point we are actually getting this g power I is 0. So, somehow these two examples motivates us to define what is called solvable Lie algebra. So, first we will define what is called derived Lie algebra, derived series. So, what is derived series? That g I that we saw, that is called derived series. Okay. Called derived series. So, how it is defined? It is defined inductively. So, you start with g and then you take g 1 to be the derived algebra. Suppose g power I is defined, then g power I plus 1 is defined to be the derived algebra of g power I. Okay. So, that is how one defines what is called derived series of g. So, where g is given Lie algebra. So, now what is solvable Lie algebra? So, it must have been clear. So, what is solvable Lie algebra? So, a Lie algebra, G is said to be solvable if g power I is 0 for some I in n. Okay. So, now let us actually prove some basic properties of these solvable Lie algebras. So, here I will make a proposition. So, we can actually prove the following. Let G be a Lie algebra over C. So, then if G is solvable, then any subalgebra of G is also solvable, and any quotient of or any homomorphic image of G is also solvable. Okay. So, let us verify this. If K is a subalgebra, then it is not hard to see this derived series K power I is contained in G power I. So, that implies whenever some G power I is 0 implies K power I is 0. Similarly, if pi is a homomorphism which is surjective homomorphism, then that would imply that pi of g of I is equal to g dash of I. So, that means whenever some g power I is 0, that will imply g dash power I is also 0. So, this proves that any subalgebra of solvable and any homomorphic image of solvable Lie algebra must be solvable. So, now let us look at the second statement. If I is solvable ideal in G and G mod I is also solvable. So, then we can say that G must be solvable. Okay. So, let us see how one can prove. Let us fix this canonical homomorphism from G to G modulo I. So, now let us say G mod I power n is 0. Okay. Say G mod I power n is 0. So, that means pi of g power n must be 0, okay, because pi is surjective. So, that would imply that g power n is contained in I. So, let us say I being solvable, that I power m is being 0. So, then that would imply that g power n power m, so which will be g power n plus m, which is contained in I power m, which is 0. So, that proves g power n plus m is 0. So, that proves G is solvable. Okay. So, now we will actually see the third statement that says about two solvable ideals. Suppose I and J, they are ideals inside G. So, they are solvable ideals, let us say. Then what we can prove? We can prove that I plus J is also solvable. So, the product I j will be again solvable, okay, because product I j will be contained in both I and j. So, that will be solvable, because any subalgebra solvable is solvable, but I plus j is a superset. So, we have to verify that is solvable. So, how one can verify? We can use this one of the isomorphism theorem. So, that tells if you take I plus j mod j, so that will be isomorphic to I mod I intersection j. So, that implies being a quotient of this I mod I intersection j, okay. This is quotient of I, being a quotient, this I plus j mod j is solvable, okay. So, this implies I plus j mod j is solvable. Now, since j is solvable, so we get I plus j is solvable using the second statement of the proposition. So, this proves I plus j is solvable. So, that completes the proof. Now, this proposition is actually allows us to define what is called a radical of a Lie algebra, because what we indeed proved, if you start with any two solvable ideals, then their sum is again solvable, okay. So, that actually kind of tells us that if you take what is called maximal solvable ideal, then that must be unique, okay. So, let us see why it is unique. Let us start with G. So, this is an arbitrary Lie algebra over complex numbers. So, here are everything is finite dimensional, okay. So, that is something one should always have. So, if you start with this arbitrary finite dimensional Lie algebra, so since this 0 space is actually an ideal inside G, which is also solvable ideal. So, one can talk about what is called the maximal solvable ideal, okay. Let us talk about A maximal. So, you pick I to be a maximal solvable ideal inside G. So, that exists using Jones lemma, you can check, or otherwise you can use here everything is finite, okay. So, there will not be any problem in choosing this maximal solvable ideal. So, now what we claim, this maximal solvable ideal must be unique, okay. There are no other maximal ideals. Why? So, claim is what? Claim is I is the unique maximal solvable ideal in G. So, let us start with some other ideal J, let us say also maximal solvable ideal in G. So, then what happens? One can construct this I plus j. So, this is also solvable and ideal, okay, inside G. So, now note that this contains both I and j. So, since I and j both are maximal, that would imply that I equal to I plus j equal to j. Okay. So, this proves that I must be unique. Okay. So, this unique maximal ideal we denote it by what is called radical of g. Okay. The radical of g is by definition the unique maximal ideal of g. Okay. So, now we are ready to define what is called semi-simple Lie algebra. So, here is a very important definition, what is called semi-simple Lie algebras. So, what they are? So, a Lie algebra G is said to be semi-simple if the radical of the G must be 0. Okay. So, let us see some examples. So, if you take any simple Lie algebra, that must be actually semi-simple. Okay. So, example 1, if G is simple Lie algebra, then G must be semi-simple. Why this is true? Because since G is semi-simple, sorry, G is simple, so that would imply that the bracket GG must be non-zero and G must be equal to GG. Okay. So, that means G will never be solvable. Okay. G is not solvable, because if you look at the derivative series, then every time you get G only. So, as G power I will be equal to G. Okay. So, that is why it will never be solvable. So, if you look at the radical of G, this is an ideal inside G. Okay. So, either it is 0 or full. It cannot be full because G is not solvable. So, that will imply the radical of G must be 0. Okay. So, that is why all these simple Lie algebras, they are all semi-simple. So, we will see sorry, if you take even the trivial space, so that is also semi-simple. Okay. But there is a very abstract way of constructing semi-simple Lie algebras from any arbitrary Lie algebra. So, that is I will list it as 3. So, let us say G be some Lie algebra, then it is easy to see if you take G modulo radical G, that must be semi-simple. So, why it is semi-simple? Let us look at G modulo radical G. Suppose it has some ideal which is actually solvable ideal. So, the radical of G modulo radical G is being non-zero will imply the radical of G modulo rad G being non-zero will imply G mod rad G containing some solvable ideal. Okay, let us call that is J modulo rad G. So, this is the solvable ideal. Okay. And this will be non-zero. So, here I have already used this correspondence between the ideals. Okay. Any ideal of this G modulo radical G will look like J modulo radical G for some J which is an ideal inside G. Okay. So, now if you look at J, so J must be solvable. Why? Because both J modulo radical J, radical G and radical G are solvable. So, that tells us that, so this J must be solvable ideal. So, that means J must be contained in the radical G. So, that will imply J modulo radical G must be 0. Okay. So, that proves that the radical of this G modulo radical G must be 0. Okay. So, this proves that radical of G modulo radical G is 0. So, that implies G modulo radical G is semi-simple. Okay. So, now I will actually, so this way of argument actually gives us some easy characterizations of this semi-simple algebras. So, let me just state it as a theorem. Okay. If G is semi-simple, if and only if G contains no solvable ideal other than 0, if and only if G contains no abelian ideal other than 0. Okay. So, the first thing is just a definition. So, we will prove that G is semi-simple if and only if G contains no abelian ideal other than 0. Okay. So, what is the proof? So, suppose G contains some non-zero abelian ideal, then that would imply that G contains non-zero solvable ideal. So, that will imply that radical of G is non-zero. So, that means G is semi-simple will imply G contains no abelian ideal other than 0. Okay. Now, for the other way, assume that G contains no abelian ideal other than 0. So, then we want to prove that G is semi-simple. Suppose G is not semi-simple, then the radical is non-zero, but radical is being abelian, radical is being solvable. So, there will be some k such that when you take radical G power k which is 0, but radical G power that k minus 1 is non-zero. Okay. I can choose a k such well. But note that the radical k minus 1 is actually, if you take the bracket with itself by definition of this derivative series. So, this is nothing but radical G power k. So, which is 0. So, that says that radical G power k minus 1 is abelian. Okay. Ideal inside G. So, that means G cannot be semi-simple. So, that proves that G is semi-simple if and only if G contains no abelian ideal other than 0. Okay, later we will actually use such important characterization, okay, to understand more about semi-simple algebras. So, now finally, I would like to actually define what is called this nilpotent algebras. So, now nilpotent algebras they are motivated from what is called lower central series. So, let me just define what is called this lower central series. So, the lower central series again defined inductively. You start with G 0 to be G and then G 1 to be the bracket G G and then G 2 to be the bracket G with G 1 and so on. So, now once G n is defined, then how you define G n plus 1 is just to take bracket with G with G n. Okay. So, that will be called lower central series. You say something is nilpotent. So, we say G is nilpotent if g power I is 0 for some I. Okay. Maybe I will include 0 as well. So, 0 space is always included. Okay. So, for I in G plus. So, now note that, so this G power I is contained in contains G power bracket I. This is true for all I. So, that implies nilpotent algebras are always solvable algebras. Okay. So, basically what we have, so we have this abelian algebras, and then nilpotent algebras contains abelian, and then we have this bigger class of solvable algebras. Okay. So, on the other side we have what is called this semi-simple algebras. So, that is just one separate class. So, let me just motivate you why these classes of Lie algebras are very important. Okay. So, to motivate that, we need to recall what is called Levis theorem. Okay. So, which will be like if I get enough time, I will be able to give proof of this Levis theorem. But anyway, let us see what is Levis theorem. So, the Levis theorem actually states that any finite dimensional Lie algebra G over C is a direct product of is a semi direct product of what is called the solvable Lie algebra, which is the radical part of G, and the semi simple part of G, which is the G modulo radical G. So, what I mean by that, given G, you have naturally two Lie algebras associated with G. One is what is called radical. So, this is solvable Lie algebra. Okay. And there is this quotient G modulo radical G, which is semi simple Lie algebras. So, what is Levis theorem says? So, G can be constructed from this radical G and this G modulo radical G. Okay. This is the semi simple part of G and this is the solvable part of G. So, G can be constructed from these two. Okay. So, that means G is a semi direct product of radical G and G modulo radical G. Okay. So, note that radical G is an ideal inside G, but this G modulo radical G, so there will be a copy of that inside G as a subalgebra. Okay. So, that is what so that means this G modulo radical G will naturally act on radical G, and then using that action one can define what is called the semi direct product, and that semi direct product will be isomorphic to G. That is what Levis theorem says. So, this is a very important theorem in finite dimensional Lie theory, because this immediately actually brings you to like if you are interested in classifying finite dimensional Lie algebras, then using this Levis theorem one immediately can focus on classifying solvable Lie algebras and as well as classifying semi simple Lie algebras. Okay. The classification of semi simple Lie algebras, it is a very complete theory. So, done by Cotton and Killing. Okay. So, but this classification of solvable algebra is somewhat, it is not that easy, and it also gets kind of very ugly. Okay. So, we will not actually focus on this classification of solvable algebras in this course. We will only focus on the classification of semi-simple algebras in this course. Okay. So, I will actually stop now. So, maybe in the next class we will actually see some of the properties of this nilpotent algebras, and then later we will actually prove some important theorems about the structure theory of nilpotent and solvable algebras. Okay, I will stop here. Thank you.